Welcome to the chapter of half-life, propagation and termination part 2 under the head of radical chain polymerization. So, if you recall that in the previous lecture we have studied about the stability and half-life of different initiator. We discussed about the mathematical equations which are attributed to the half-life of different initiator. We had a discussion about the dependency of polymerization rate on initiator, how these initiator play a vital role in the rate determining steps of polymerization process. We are discussing about the dependency on monomer with respect to the initiation in the aqueous media. So, and in that particular edges we were discussing about the redox reaction which are very important in the polymeric system. Let us continue with this particular topic which is attributed to the redox initiation. So, we can say that virtually all radical chain polymerization reaction, they require a unique and independent initiation step in which free radicals are generated in the reaction system. If you recall, in the previous lecture we discussed about the generation concept of those free radicals as well as what are the importance of those free radicals, especially in the propagation, especially in the with respect to the termination step. So, that is why they require a unique and independent initiation step. Now, this initiation step is very critical, and the activation energy barriers, they play a very important role during the selection of initiator compound, because sometimes the question may be triggered in our mind that what are the selection criteria for the different kind of initiation. Though we have discussed several issues related to this in the previous lecture. But sometimes if you say that activation energy barriers, they play a very vital role. So, the type of initiation process to be used for a specific polymerization process usually being determined by the activation energy barrier concept plus what kind of a different initiator you are using for your polymerization step. Now, we had a discussion about the bond dissociation energy attributed to the initiator, so that the free radicals may get generated in due course of time. So, the bond dissociation energy limit for various covalent breakage maybe in the range of say 100 to 170 kilojoule per mole through the thermal initiation reaction. Now, this energy limit is very low or very narrow. Therefore, it limits the use of various compounds having activation energy above or below this limit. So, this is one of the limiting factor which you can say for the choice of initiator. Now, second important parameter which we would like to discuss is that the concentration of a free radical present in the process, which if increased to a substantial amount can lead to unwanted reactions such as primary termination or self combination. Now, these two things as you recall that they are very important especially in case of polymerization process. Now, because sometimes they may not perform the duty of initiation for which they are designed to, because of the primary termination, and sometimes they may go for self combination, so that practically they are dead in nature. So, that is why this concentration role play a very vital role, and if you recall in the previous lecture we discussed the Ki, which is the rate constant for the initiator, the concentration of free radical. So, you have to be very particular about this particular this aspect that is attributed to the concentration of free radical. Now, let us have a look about the redox initiation. Now, redox initiation is another kind of initiation phenomena where electron transfer carried out between the two molecules through oxidation reduction reaction, and then the bond dissociation may occur at the acceptor molecule to generate the free radical. This again poses one more opportunity for the initiation of polymerization reaction. Now, redox initiation, or sometimes it is termed as redox activation, they found the several application in the polymerization process or in the commercial scale. So, it is always favored for conducting low temperature emulsion polymerization. So, more and more application it is attributed to the low temperature emulsion polymerization. Now, these redox initiator have advantage of lower activation energy. If you recall that previously we discussed about the higher activation energy concept. So, they are having the advantage of lower activation energy for initiation reaction, and they can produce radical to a substantial amount over a wide range of temperature range. So, they are having a very wide spectrum related to the polymerization reaction. Now, because of the low activation energy that is in the range of say 40 to 80 kilojoule per mole, the redox reaction or redox initiation can conduct the chemical reaction at moderate temperature range, maybe below 50 degrees Celsius or even lower than 0 degrees Celsius. So, this is one of the plus point which the redox initiation process they offer. So, this requirement of a lower activation energy usually reduces the possibility of any kind of a side chain reaction and increase the yield. So, it helps in twofold. One is that in case of a formation of any side product or any byproduct, then you may encounter the problem of a separation and your yield may go down. But because of this low activation energy, the possibility of formation of those side products or byproducts are minimal. So, in that case you may it may help to increase the yield. Additionally, you may say that these reactions have a very short induction period, hence the reaction proceeds quickly, and that is why this particular approach is very much popular in some of the industries, because the short induction period offers low economic burden to the industry. Now, they are having certain limitations too, like lower efficiency than the thermal initiation, and that is again a very challenging approach, and complex control of initiator, because we discussed that the initiator play a very vital role, and especially sometimes they may induce for the self combination, they may induce the dead of to promote the deadly character of monomer radical. So, the control of those initiator is extremely important. In that particular approach, these redox reaction have certain limitations. Sometimes the addition of charged metal ion and counter ion can affect the electrostatic stability of the system. So, these reactions are also the pH sensitive. So, therefore, usually weak acids are used for performing any chemical reaction. Now, the pH sensitivity is again pose some limitation to these type of reaction, because sometimes you are using certain acidic media, certain base media to carry out the polymerization reaction. So, you have to be very particular, you have to be very case sensitive, you have to be very cautious while carrying out this type of initiation reaction under the edges of radical chain polymerization. So, these type of things are extremely important to be looked into. Now, let us move to the initiation process in the aqueous media. So, we will discuss several aspects related to the this aqueous media, because aqueous media play a very vital role in the radical chain polymerization. So, first step in this category is lead to the peroxide concept. Now, hydrogen peroxide H2O2 is a well known and very commonly used chemical for the production of hydroxyl free radical. See, in the previous lecture we had a discussion about this concept of hydroxyl free radicals, and how they facilitate the radical chain polymerization. So, this hydrogen peroxide, it's a very common chemical used for the production of such kind of a free radical. Now, these hydroxyl radicals, they have a very high oxidation potential, around 2.8 volt. Hence, we can use as a chemical in wastewater treatment for mineralizing various persistent pollutants, etc. So, it is a very common thing for as a bleaching agent in the chemical operation or a chemical processes. Fenton's reagent again, which is combination of a ferrous salt and hydrogen peroxide. It was discovered in H.J.H. Fenton in 1894. Now, he reported that the hydrogen peroxide can be activated by ferrous salt to oxidize tartaric acid. So, this was a very good study, and it attributed for the major problem in the wastewater, the paraphernalia. Now, it involves the reaction of peroxides with iron ions to form the active oxygen species. Now, let us discuss some of the reactions which can better show the mechanism, what kind of mechanism involved, and these mechanisms are equally important in the polymer reaction engineering, especially with respect to the radical chain polymerization. Now, this is the peroxide radicals through Fenton's reagent. Now, let us take first example, that is the oxidation of ferrous ions to ferric ions to decompose H2O2. So, if you recall that our main intention is to produce this hydroxyl radical. Now, here this Fe2 plus H2O2, this gives you plus OH minus plus OH radical. Now, here the rate constant, that is K1, is somewhere around 40 to 80 mole inverse second inverse. Now, this generated Fe 3 plus ions can be reduced to Fe2 plus by Fe3 plus H2O2, Fe2 plus HO2 plus H plus. Now, here the rate constant K2 is around 9.1 into 10 to the power minus 7. Now, the rate limiting step where this OH radical can be consumed, this can be written as whenever we talk about the rate limiting step, then it can be Fe2 plus OH radical, then 3 plus OH minus. Now, here the rate constant is K3, 9.1 into 10 to the power minus 7. Right. Now, this another Fe2 plus HO2 radical, this is 3 plus HO2 minus. Now, here the rate constant can be written as 0.72, 1.5 mole inverse this one. Now, this Fe3 plus HO radical, HO2 radical, Fe2 plus O2 plus H plus. So another rate constant which is in the range of 0.33 to 2.1 into 10 to the power 6 minus 6 mole inverse. So this is now if you see that the generated radicals that is and can also react among themselves or with H2O to H2O2 to produce less oxidation potential compounds. So whatever we have generated in the previous equations, they can also react on their own to form either H2O2 or other less oxidation potential compound like this, that OH radical may combine with this radical to give you H2O2. Similarly, OH radical may combine this hydrogen peroxide which generated over here to give you this radical. And similarly, another option is H2O2 plus O2. So these radicals, although they produced during the course of this combination, but they are very less effective compared to the previous one. So similarly, as discussed for H2O2, this Fe2 plus ion can also be used for the decomposition of alkyl allyl compounds. Now let us take the example Fe2 plus ROR RO minus plus this radical being produced, and similarly Fe2 plus it can give you this radical to give plus R minus. So this is the basic concept or basic mechanism of Fenton mechanism which we discussed here. And if you see that this particular concept is extremely useful in radical chain polymerization. Now apart from this, another important concept is attributed to the persulfate. Now the similar type of reaction which we discussed previously, they can occur for various disulfides, persulfates and elemental hydrogen compounds. Now let us have a look about this particular approach like for the persulfate. First example is that this one, they can combined with this Fe2 plus may give you plus this radical, and similarly it can give you O3s bonded with this one, and Fe3 plus O3 SO radical, this one is negative charged, and SO4 minor. Similarly, if you take another example like this, this may give you SO4, and if you take another halogen substance in question, Br2 plus, it may give you Br radical plus Br ion. So sometimes this Fe2 plus which you can be replaced with silver ion for S2O8 2 minus in this equation. This is again a very important thing. So, these persulfate they can also form the redox system with several oxyacids to generate the free radicals, and which we discussed that persulfate can initiate the polymerization reaction in the absence of hydroxyl radicals due to their good scavenging properties. Let us give an example related to this particular concept and in continuation with the previous handout, that is O3SOO, SO3 negatively charged, then this silver ion combined with this, and this is sulfate ion plus. Now, similarly, if you take another reaction into consideration, cut it. No, it's okay. Start. Yeah. O3S, it is combined with the O, bonded with the oxygen. Now, this gives you Ag3 plus SO4 2 minus plus O3SO radical. Now, at last you may get Ag3 plus twice OH ion. This may give you Ag plus 2 HO ion. Now, this is again produced the radical, which is again very important thing need to be addressed. Now, we were discussing about the persulfate with the oxyacids. So, let us have another example related to this, that is persulfate with oxyacids. So, persulfate whatever we generated in the previous slide, S2O8 2 minus plus SXO4 SO4 plus SO4 2 minus plus SXO4 N minus 1 negatively charged, and similarly, so SO4 minus negatively charged plus HOH HSO4 negatively. Now, both this SO4 negatively charged and SXO4 N minus 1 negatively and radical can initiate the polymerization. So, this is the way through which you can represent. Now, this however will with increase in the lower oxidation potential, the thioradicals such as S2O3 negatively charged, the polymerization should initiate with the OH radical. Now, let us have a brief outline about this one, that is S2O8 plus S2O3 plus S2O3 plus SO4, and this SO4 plus H2O may combine together to give you HSO4 plus OH radical. So, this is again this reflects the initiation process in aqueous media. Now, at last we can discuss about that monomer that can act as a redox pair with the persulfates include. Now, ascorbic acid to generate ascorbate radicals for acrylonitride polymerization in air atmosphere. It is a very useful thing and it is very important concept. thiamalic acid with the peroxide disulfate in nitrogen atmosphere for the polymerization of acrylonitrile. Then it can be used in the persulfate radicals can be used for the polymerization of acrylamide, and mercaptans can be used for the vinyl polymerization. So, these are several examples attributed to the in which the monomer can act as a redox pair. Now, the rate of polymerization reaction usually depends upon the selection of initiator species, and we discussed this thing that what is the importance of this selection protocol during the polymerization of radical chain. Now, let us have an example for this particular approach, that if ascorbic acid peroxide disulfate redox pair is used for the polymerization of say acrylonitrile, the rate of reaction usually shows the dependency on the square of monomer concentration, which we already discussed in the previous lecture, that how the rate constant or rate of the reaction depends, or rate of dissociation of initiator depends on. So, the square of monomer concentration, the first order of ascorbic acid, and the half order of peroxide disulfate concentration. So, RF they have discussed this particular concept in 1985. Now, while if thiamalic acid peroxide disulfate redox pair is used for the polymerization of acrylonitrile, the rate of a reaction usually depends on the first order of monomer concentration and 0.4 on thiamalic acid and 0.6 to say 0.75 on peroxide disulfate concentration. So, this was again discussed with Tajuddin in 86, and they found out these values through the extensive research being carried out by them. So, in this particular lecture we discussed about the initiation under the edges of aqueous media. We discussed the various mechanism, we discussed the various research findings being carried out by the noted workers in the SAT field, and if you wish to have further reading or further knowledge, or wish to go into deep, you can refer to these references which are enlisted in this particular slide. Thank you very much.